Hey everybody, Professor Ghassemi here. This week we'll be speaking about databases and how databases are used to power web applications. As usual, there are some suggested readings, and actually beyond those suggested readings, there's actually a set of pretty cool resources that I've linked to in the Git repo this week. Do encourage you to check those out. As always, they contain some of the source materials that I used to create the lecture. So if any of this you want to go into greater detail, I do encourage you to take a look at what's there on the Git repo. Okay, so let's jump in with a conversation about relational databases, which is the technology that we will be using in this class. Before we jump into that, let's just take a step back and recall something we discussed last week. Our objective is to learn how we build a dynamic web application. And a dynamic web application is, once again, an application where when our client makes an HTTP request to our web server, that web server passes along the request information to a web application, which is some server-side code. In the lecture last week, we discussed how we could use Flask plus Jinja to do some of that server-side coding and to leverage HTML templates to generate dynamic content that could be sent back to the web server. But what we didn't discuss last week was this blue database here in the bottom left. Basically, the web applications that we went through in an exemplary fashion last week didn't touch databases at all. This week, we're going to be speaking about this database component, which is actually incredibly important if you want to have any information that persists on your users and supports your application function, which is effectively any real web application. Okay, I want to say as well what the purpose of these database systems are. Okay, a database is not data. A database is something that sits between you and the raw data that sits on the disk, and it provides a way to facilitate the storage, retrieval, modification, and deletion of that data. It's supposed to make your life easier by having a relational database management system. Okay, so just understand that there is a distinction between that system and the data itself. There's also a variety of different kinds of databases. There is relational databases, that's illustrated by this table that we have in the top left. There are analytical databases, key value databases, which are, as the name implies, databases where a key is provided. Those are what's kind of mapped. And then a set of value or a document could come out the other side. You have column family, graph databases. These are used often when you want to organize information about networks, like social media data is sometimes organized using graph database. And then you have document style databases, like what appears on your hard disk, right? You have folders, those folders have subfolders, those subfolders have further subfolders, and so on. All of these are different kinds of databases, and ostensibly for your web application, you could really use one or more of these. But for our purposes, we're going to be talking about relational database systems, and there's a good reason for this. Firstly, it's the most widely used kind of database system. So what I've got here is a ranking of database systems that comes from dbengines.com, which I encourage you to take a look at. It's a really neat website. And what it does is it lists all database management systems as of March 2022, when this lecture was made. And if you just glance at the top four, all of them are relational database systems, followed by a document store system, followed by a key value system, again, then a relational, and also in the 9th and 10th places, relational databases. The point I'm trying to make here is that you won't be able to escape relational databases. And furthermore, many systems actually assume some familiarity with them. Now, escape might not even be the right term here, because I hope to convince you by the end of the lecture that they're actually really useful for a huge number of use cases and purposes. There's a couple of things that they're not really built for, which I'll also touch on as we go through the lecture. So let's talk a little bit about this relational database model and what are the kind of defining features, the pros and the cons. Well, What's nice about relational databases is they just have effectively two defining features. The first is that data is stored in tables, like this example I'm showing on the right. We might have a table 1 that contains some information about products, a product code, a description, and a price. And then we might have a separate table that contains some information about invoices. We might be having people pay for those products, and we want to keep some information in an invoice. So we'd have an invoice code, an invoice line, a product code, and a quantity. And so a relational database is just consisting of these tables, like I'm showing you here on the right, and some kind of common or shared field between them that indicates what maps to what. So in this case, it's the product code, right? This first column in table 1 maps to the product code in table 2. And in this way, I can kind of tie the information in table 2 to the information that's in table 1 if I wanted to. I could sort of cut this row out and glue it onto the row here if I needed to. Okay. So the pros of this kind of structure, the relational database model, is that you can add new relations very easily. If, for example, I had some auxiliary information on, I don't know, discounts that I wanted to add, all I would need to do is create a new table, maybe table 3. I could include the invoice code in that table and include some information about discounts, right? And so I wouldn't even need to modify table 2. I could just use a code or a column that exists in table 2 to inform something about a new kind of table that I'm going to create. And that's really convenient. So new relations can be added very easily. And also those changes, of course, can be made to the database schema without affecting what's happening in the data completely. Now, of course, every model, every system is not perfect. They have pros and they have cons. And there's two major cons of relational database models. The first one is that it usually assumes some structure of the data is known in advance. Okay, so what this means is that when you're creating a relational database model, you usually put together tables like you see here, and they may not have any data in them initially, but you've sort of specified the column headers ahead of time. Usually, but not always, that's the way they're built. So that's great if you know what those column headers are ahead of time. It's not so great if you have no idea what those column headers are, or those column headers could change depending on the client, let's say you're working with, or the kind of problem you need to solve, and so on. So for those kinds of issues where you don't really know exactly what the structure is, or the structure could be a very nested and hierarchical, sometimes NoSQL databases are preferred for those cases. The second kind of instance where relational databases have some cons, I would say, is when you're dealing with data that has a lot of complex, nested relationships. And relationships is the key word here. Think about modeling a social network. You could have two entities, and those two entities not only have just a relationship, but they have a particular value that governs that relationship. They could be friends, they could be friends and siblings, they could be friends and siblings and business partners. And then, of course, each of the entities themselves has a number of parameters. And the way that the tabular kind of relational nature of how things are set up in a relational database system are not always the most straightforward for representing that kind of complex nested relationships. You can represent them. It's just not as easy as if you were going to use, let's say, a graph database. So I wanted to start off here by just telling you, just very simply, what is a relational database model? What's the good part of a relational database model, and what's the bad part? Okay. Now, relation is in the name of relational database. So I think it's worth starting off by talking about the different kinds of relationships that can exist. There's really three. There's a one-to-one, there's a one-to-many, and a many-to-many relationship that can define how tables are interconnected or related. Let's look at a couple of examples. So of a one-to-one relationship, that basically means each instance in a first table has a relationship with only one instance in a second table. So for example, if we had a field husband in one table and we had a field wife in another table, that would be an example of two fields where there is a one-to-one relationship. Okay, so every husband has one wife and every wife has one husband, as an example. Okay, there's also one-to-many relationships that could exist in relational databases. What this means is that each instance in the first table might have a relationship with multiple instances in a second table. So for example, we might have a table that contains some information on a sculptor, and that sculptor might have some sculptures that they have created. Well, it would make sense to sort of store the sculpture information in one table and the sculptor information in another. And there'd obviously be a many-to-one relationship there because a sculptor can create many sculptures, but a given sculpture only has one sculptor. Okay, and then of course the third kind is a many-to-many relationship. This is, so for each instance in the first table, there's many instances in the second table, and for each instance in the second table, there's also many instances in the first. Good example of this is if you have two tables, one with students and one with lecturers. Well, a student can have many lecturers in the lecturers table, depending on what classes they're taking as an example. But a lecturer can also have many students. And there's not necessarily a parity when you go from students to lecturers is what you get from going from lecturer to students. Okay, so these are the three kinds of relationships that you'll see in relational database systems. Okay, now the core components of a relational database are really these 5 items. These are terminologies that you will see used to describe the systems, and if you understand what these are, it will make some of the stuff we do with SQL and the practical implementation work later a lot easier. First one of these is a table. This is just a collection of data entries that are stored on your disk. It consists of rows and columns. Very straightforward. We've seen an example of that. The second of these is a field. That's when you go to a given cross-section, a given row and column intersect, that is a field. Okay, those fields could have a value that's governed by some type, or they could be null. The third thing is a view. This is sort of a virtual table. It's not stored on your disk per se. It's a virtual table that's constructed ad hoc and on the fly using a subset of other actual tables that are stored on disk. Fourth one is a key. This is sort of a logical structure of your storage. It identifies the rows in your tables. And then the last one is an index. And an index is like a key, except that instead of just being a logical structure that identifies rows in your table, it actually dictates physically how information could be stored on your disk, which has implications for how quickly you search that data and how quickly you retrieve it, insert into it, and so on. Okay, so let's step through each of those items in a little bit more detail so it's concrete. When we're speaking about tables and fields, the fields really are consisting of, I would say 4 types mainly. There's actually more than 4, but the way to partition it in your head is really into 4. There's sort of numeric fields like int and floats. There are text fields, varchar and text. There are temporal fields like date and timestamp. And then there are what is sometimes called blob fields, which is kind of a catch-all for everything else, images, PDFs, and so on, that you might want to store in a database. Okay, now tables and their relationships, as well as the fields, are often represented by what's called an entity relationship diagram. And if you Google around or search the web, you're going to see lots of these kinds of entity relationship diagrams that are meant to describe how the tables are related and what the contents of the tables are. In this particular case that you see on the right-hand side, I generated this actually using this my.vertablo.com, which I encourage you to take a look at. You can sign up for free, and it's a pretty cool way to actually create a schema and layouts for your tables, indicate the keys, the indices, and so on, all visually, and it will actually generate SQL statements for you later. But anyway, what this is meant to show you is if you had 3 tables, a client table, a city table, and a country table, and these tables each have some fields. In the case of the city, for example, it has an ID, it has a city name, and a country ID that is an int, a varchar, and an int respectively. This city has a one-to-many relationship with clients that exist, which makes sense, right? And similarly, a country has a one-to-many relationship with the cities. Okay, so this is sort of a way that you will see information about databases represented and laid out. It's a great way to understand the schema of a database and the contents that exist within it. Okay, so we spoke about tables and fields. Let's also speak a little bit about views. Remember, views are just virtual tables, so they're only a structure. They don't technically contain any data. They're just meant to generate versions of your data that are easier to use and visualize. Keep in mind as you're creating views that they are computationally expensive. So each time a view is referenced, it's generated on the fly, and a bunch of computation is used to generate it. So why would you use a view? Well, there's a couple of reasons. I think that the one on the right-hand side is a good illustration of this. Let's say you have a table that has some, let's say, sensitive information in it. Okay. Let's say you have a student table and it contains an address and a telephone number that you may not want to expose to some user. Well, what you could do is you could create a view here that basically selects a subset of those. And so when people query the view, it effectively not gets rid of, but excludes the information that is sensitive in that root table. That's an example of why you might want to use a view. There's other reasons, including kind of containing very complex queries that you might want to perform on these, join operations and so on, things that we'll be speaking about a little later in the lecture, within a single table for analytic users and so on. Okay, so we spoke about tables, fields, and views. Let's speak about keys next. The key is what governs the relationship between the two tables. Okay, it's a column in one of the tables that ties it to a column in another one of the tables and therefore allows you to glue those two tables together. For the purposes of this class, I'd like you to think about keys as being of two kinds. There's primary keys, and these should always serve as the unique identifiers for each row in a table. So one table only has one primary key. Okay, it should be an ID, a unique ID for that row. That's the way to think about it. Okay, and then you can have foreign keys. These map a unique identifier in a different table. So if we come back up a couple of slides just to be clear here, in this client table, you can see there's an ID, right? And within this, there is also a city ID, okay? Notice that this ID for the client has PK to the right of it. This is indicating that it's the primary key of this table. So what that means is that for every distinct row in this client table, there is a distinct numerical integer value for the ID there. But it also has another kind of key that ties it to the city ID in this table. And notice that when a key is a foreign key in this table, it must be a primary key in some other table. In this case, very logically, it is the primary key in the city table. Okay, so there are these two kinds of keys. There's the primary keys and there's the foreign keys, and that's sort of, they're used to create the relationships across tables in the case of the foreign key, and to govern the uniqueness of a given row within a table in the case of the primary key. Okay, another thing to note about keys is that they can be attached to single attributes or can be composites of multiple attributes, meaning that you don't have to have actually a dedicated column called ID and attach a primary key to it, although that's a common thing to do. You could technically specify a set of attributes in your table, like two columns, and those together, insofar as they uniquely identify the contents of a given row, and they always uniquely identify the contents of a given row, those could be used as the key for your table. Okay. Just to make things a little bit more clear, even though we talked about this, I'll touch on it again. If we had, let's say, these three tables, a student table, a course table, and an instructor table, the student table, the primary key would be this column here on the far left. You notice that the student ID number is never the same. It's always different, one for each student. It uniquely identifies the row. The student table also contains a foreign key, which maps to the primary key of the course table. Okay. What's the dead giveaway that it's a foreign key? Well, notice that it's not unique. You have two CS2s, you have three CS1s, you have a CS3, and so on. In addition to the fact, of course, that this name is not the same as the name of the table. okay? But notice that this maps to the three distinct values for CS1, CS2, and CS3 in the courses table, which itself also has a foreign key to a instructor table, the instructor ID in this case, which has information appropriately on instructors. So if you understand this simple example, you sort of have got the difference between a primary key and a foreign key and what they're meant to do when you're designing relational database systems. So there's an idea when you're dealing with keys called referential integrity. And this is meant to ensure that for every foreign key entry in a child table, there's a corresponding primary key present in the parent table, meaning that you can't make this batch ID a foreign key here unless it actually is the primary key in another table, meaning it has that for every one value in this, for every unique value of the batch ID in the batch table, there has to be exactly one row that maps to it. If there was more than one, it would break the referential integrity and you would not be able to use this as a foreign key. It doesn't mean you couldn't still combine them. You just couldn't combine them using a foreign key mechanism. So just to be clear about that distinction. Okay, we've spoken about, we've spoken about fields, we've spoken about tables, we've spoken about views, and we just got done speaking about keys. Well, that leaves indices or indexes. Okay, an index is just, the way to think about it is it's a copy of a column or a set of columns that you kind of order so that you can increase the speed of database retrieval operations. Okay, they're really useful if you're going to be doing a lot of selecting, a lot of read operations on a database. So if you have a very big database, you very rarely insert into it. That's the kind of thing that indices are going to save your life. However, if the database has a lot of write operations, it slows down. It doesn't slow down your database when you're reading it, but it takes more work to insert into that database because you have to update that index. Okay, what an index basically does is it will take some data like what you see on the right-hand side that has, I don't know, let's say an employee name, an ID, and a department that's in no particular order, and it will generate a search key like you're seeing there on the left that says, hey, where in this table is, Alex, David, and Greg, so that you can very rapidly find that information in some order that you care about. Okay. Now, when you're generating indices, there's two ways to generate them. You can either use a B tree or a binary tree. This is sort of the default in a lot of database systems. We'll be using MySQL, but a lot of other systems also just by default use a binary tree. The reason that that's the default is because although it's not as efficient for finding a given record as the hash is, which we're going to talk about here in a second, it allows you to do operations or searches across ranges that you might be interested in, which is a common downstream analytic operator. If you're using, for example, an order by clause in a SQL statement, which again we'll talk about here in a minute, using a B tree is much preferred. Now, there could be, of course, some circumstances where you'd want to use a hash index instead of a B tree. Specifically, you'd want to do that if you want to find a given record very fast, but you don't ever need to look across a range of records, because obviously hash is O log 1 and B tree is O log n. So you could do a given search much faster in a hash if you knew what you were searching for in the table than you could with a B tree. But again, ranges would be precluded from that sort of an operation. So if you're going to create indices on your tables, just keep this in mind. Okay. So now what we've done is I tried to give you at a high level some idea of, what are relational database systems? What are the core components? Why should you use them? Let's think about some of the design considerations. And when I say design considerations, the specific hat I'd like you to have on is that of the integrity of your database. Meaning, there's no one correct canonical way to design a database. There's multiple ways that you could store information in a relational database system to power your web application. And so what you want to do is, as you're building or designing that database, You want to have really three kinds of integrity in mind so that as you lay out the database, it prevents downstream problems. Okay. The three kinds of integrity that people will oftentimes refer to are first what's called entity integrity. This is to say that you shouldn't have duplicate rows in your table. Okay, so let me be very clear here. I could create a table technically in MySQL or somewhere else where I allow this to happen, but that would be a very, very bad idea because when I wanted to do operators to fetch information, I could get confused between these two rows. I might update one and leave the other the same. I might not know which one is the authoritative record. So within a given table, you want to make sure there are no duplicate rows in that table. Primary keys help with that. They won't let you actually have a perfect duplicate. The teacher ID, for example, might be different if it was a primary key column, but they won't actually stop you from having a duplicate at the level of the name, the office, the phone, and the email. So you'd have to be careful of that as you're dealing with the entity integrity work on your own. There's also domain integrity. So this means making sure that the type information for these columns is adhered to and respected. Again, databases sort of take care of this for the most part for you. You can't, for example, if class ID is an integer, insert a character here like X. But you could design your database in a way where it allows you to be sloppy. You could make everything a character, and then you could have IDs that are 1, 2, X, A, B, C, D, E, F, G. That might, although it would technically satisfy domain integrity, in spirit it wouldn't. So try to design your databases by being thoughtful of the types you assign here and respecting those types as you deal with them. Okay, the last one is called referential integrity. This is that rows cannot be deleted which are used by other rows. Meaning, if you had, this is from our previous example, if you had a table that had a teacher ID here and then you had some classes that reference that teacher ID, so you have some other table that looks for this, well, you shouldn't allow me to delete this yet until I go and delete all of the stuff in those downstream tables that depend on this information or that use it somehow. Okay, you want to keep that referential integrity going. Okay, so these are sort of the three pieces that people think about when they discuss the integrity of a database design. So how does this relate to your organization of a relational database schema? Well, you don't actually have to think really in terms of those three integrity elements. There's actually a simpler process that I usually advise people to do, which is when you're undergoing what's called database normalization, try to make sure in the first order that your larger tables are split into smaller tables that remove any kind of duplication. Okay, there's some other properties as well that are important, but really it's the duplication here that matters. And I'm going to show you through this illustrative example. Let's say we have teachers here. This is from that previous slide. You see here the teacher and the class ID stuff. Okay, so let's say we have a teachers table here and it's got some information, and we have a classes table here. Well, this information contains information on both the teachers and the classes, and the total number of fields it takes to represent that is 5 by 2, which is 10, and 6 by 3, which is 18, or 28 fields in total, right? So we got all the information in 28 fields. Well, technically, we could do this all in one table, right? We could create a table that is the teachers plus the classes like I'm showing down here. And I could have a teacher ID and a class ID. And then what you start seeing is that some of the names of the professor, in this case, Professor X, and their office and their telephone number gets repeated. And what this does is it creates extra kind of redundant information. That is the giveaway that you should look for to hint to you that you need to turn this into a set of smaller tables to remove that duplication, okay? At a minimum, that's what you want to do when you're designing your database schemas, is make sure you don't have duplication like what you're seeing here at the bottom by, for instance, splitting it like we have there at the top right. Okay, so that process of trying to take your database and put it in a format where it's high integrity is referred to as database normalization. And formally, there's actually three forms of a normalized database. There's first normal form, second normal form, and third normal form. So let's speak about each of those three forms at a high level. The first normal form basically says that each filled value can only each field can only have one single value. Multiple values are not allowed. So what this means is if you had, for example, some contact numbers here in this table, see, we've got an employee number, we've got a name, contact number, and a department. What you're not supposed to do is say, oh, actually, this employee has 2 telephone numbers. You know what? Let me put those 2 telephone numbers and just put a semicolon and plop the other one in there. That violates the first normal form kind of requirement when you're building your database. You should actually break that into a separate table if that's the case, and have a contact numbers table as an example that maybe ties to the employee number and lists multiple rows, one with each contact number for that employee. Okay, that would be the way you solve that. Okay, each table column should have a unique name as well, so you shouldn't have redundant data. You shouldn't have a name of, in this case, Steve and Kitty. You shouldn't have another one that's called full name with Steve and Kitty, and so on. And each row should have a key that uniquely identifies it. So you wouldn't want to have, in a table like this, E1 show up again if you were using this as the key for the table. Okay, so that's first normal form. Second normal form when you're creating your database is, first of all, you have to satisfy everything from that first normal form that we covered on the previous slide. But then furthermore, all your non-key attributes, so things that are not your primary and your foreign keys, must be fully dependent, okay, on all your primary key and not just one of the attributes of the primary key. Okay, to be clear, if you had a composite primary key, let's say A and B, what you can't have is a situation where C and D in this table are dependent on the value of B, not A and B together, but E and F are dependent on the value of A and B uniquely. That kind of partial dependency should be moved out to a second table. Okay, and then the third normal form is you satisfy everything that's in the second normal form, but you have to also remove something called a transitive dependency. And this can be a little bit tricky to wrap your head around, so I'm going to try to step you through an example. First, the definition of a transitive dependency is that non-key attributes or no non-key attribute should determine any other non-key attributes. Again, non-key is the operative word here. So in this table on the right-hand side, let's say that the key is the author ID. And so what I want to prevent is that a non-key attribute should not be able to determine any of the other non-key attributes. This happens when A can be used to uniquely identify B, B can be used to uniquely identify C, where these are column names. And therefore, if you can walk this way, then A can uniquely identify C. Let's look at an example. So let's say we have authors and we wanted to know, well, hey, can we use the author to uniquely identify the book? The answer is no, right? Because if I knew who the author was, if I told you who the author was in this table, like Orson Scott, I wouldn't know whether the book was Ender's Game or Children of the Mind. There's no way to figure that out, just knowing the author name. But if I go from book, if I start with the book's name, I actually can uniquely identify the author, because in this particular database's case, each book has only one author. Okay. Now, that in and of itself is not the problem. The problem is that you can do a third step. Okay. Given the author, I can uniquely identify the author's nationality. But note that if this were a real table, given the author's nationality, I couldn't always identify the author. Meaning that I can go from book, knowing the book, to always figure out the author's nationality through knowing the author. That's what a transitive dependency is, and that's what you want to eliminate. It basically says, if I start from here, can I always get a mapping to a distinct author? And then if I'm here, can I always get a mapping to a distinct author nationality, a one-to-one kind of relationship? If the answer is yes, you have a transitive dependency. Okay, those are what you want to remove. In this case, the first way that you might remove that is by saying, okay, let me go ahead and break that into two tables. So from something like this to something like this. Okay, and in breaking that, now you have a book ID, a book, and an author ID, and then you have an authors table separately that says, okay, well, I've got an author and the author's nationality. Well, let's go ahead and check these, see if there's any transitive dependencies. So if I have a given book, I can't use anything here to figure out anything that's a non-key because there's only keys in here, right? So this books table is all set. But if I look at the authors table, under author, I can use actually this author ID, obviously, to reconstruct what the author nationality is. You see, it's the same problem that we had before. And so actually what you would do is you'd split this out to be books and authors and countries, okay? Which, if this whole, let me say, if the transitive dependency stuff doesn't seem super intuitive from a definitional perspective, just try to think logically about this. Would you really want to put information about countries in the same table with the information about books in the same table as the information about authors? No, like those are sort of distinct, I would say, sets of information and should intuitively go in distinct tables. Okay, so insofar as you sort of follow that that intuition, and you also do your best to make sure you don't have repetitions, you'll do a decent job even at a first pass satisfying some of these normalization criteria. Okay, so with that said, now what we'd like to do is turn away from some of these theoretical elements of, what is a relational database, what does it consist of, and what are some of the things you should think about when you're specifying the schema and laying out the tables, to how do you actually functionally work with those tables? How do you create them in a programming language and so on? And the language you use to create, interact, and operate on relational databases is called the structured query language, or SQL. SQL is another way that people often refer to it. And it can be used for creating databases and tables, and it can also be used to run things called queries that select, insert, update, and delete from those databases and tables. Okay, what I'd like to do is just very quickly take you through some examples. By the way, every single one of these examples, I did them on dbfiddle.com. dbfiddle.com is like JSFiddle, which you've seen me use in some of the other lectures, but for this one, instead of being for JavaScript, is for databases. It effectively allows you to choose a database engine like MySQL 8 or Postgres or something else you're interested in, and to kind of play around with how you would use that. Okay, you probably don't need that because you already have a Docker container in this class, and the Docker container is coming pre-installed with MySQL, so you can just use the web app that you already have. But in case you'd like a separate ecosystem where you can kind of play around with some of these SQL things from scratch, I do suggest dbfiddle.com. Okay, so let's start with creating tables. Some of this will probably mesh with what we described in the theory part of this. In this particular case, I'm interested in creating two tables, okay? And there's a couple of things I want to point out here about the syntax. The first one is you see these dashed lines, the double dash that are gray in color and everything after it is gray. This is what a comment is in SQL. So I've got, for example, here something that says create institutions table. I've got another one in here that says create positions table. And you might notice that in blue, I've got some these blue lines on 3 and 12. I've got a statement that says create table if not exists, and then I've got the name of the table that I want to create. In this case, it's institutions here and positions here. Now, within that create table statement, I specify effectively all the columns that are going to show up in that table. In the case of this institutions table, there's 1, 2, 3, 4 of them, as you can see here. And I also say some of the information about what's the data type of those columns. So the inst ID is an integer. Okay, the type column is a character, variable character string. So it can be up to 100 characters long in this case. There's also a name and a department, which are also strings. I can also specify some information about whether I want to allow these to be null or not null, or default null, as you can see here. I can specify whether I want these to auto increment, which will be useful if I've got a primary key as an example, like institution ID. And I can place a comment on them so that in case I forget exactly what this was, I can go back and read it later. So speaking of primary keys, the way that's specified here is here at the bottom, you type out primary key and then you just list what you want the primary key to be. There's some stuff down here that is not super important for you to know, but I'll try to step you through it. Database systems have things called engines that govern specific properties about how queries are run, the data is organized, and so on. And in the case of MySQL, which is the particular flavor of SQL that I'm using here, we're using the InnoDB engine. Our auto increment starts at 1 because this was auto incrementing. We've set the character set to be UTF-8, and we've put a comment on the entire table. And this sort of concludes the creation of one table in SQL. If we run this, that table will be created. It's good to go. We can start running other queries on it and so on. Now, the positions table down here has a lot of the same things that you saw in this table up here. There's just a couple of distinctions that I want to point out that are important. First, notice that unlike this first table, the institutions, which only had integer and varchar data type fields, here we have date type fields. Okay, so start date and end date are listed here. Also notice that I was speaking about foreign keys, remember? And here it is. You can specify a foreign key in this table. And when you specify a foreign key, you can say what specifically it references. I do want to note here, if you want to have two tables that have a shared, let's call it a key, so a column in one identifies information in another, you don't have to call it a foreign key. You don't have to write foreign key there. You could still join. You could do all those operations without the foreign key. But if in fact you wanted to join on two tables and there's a primary key in one that you want to use for the purposes of joining, you should use a foreign key because it helps with that referential integrity that I mentioned earlier. So you don't have to include a foreign key. You know, it won't prohibit you from doing joins or merging information across the tables. But again, if the thing you want to do the joins with later are primary key in that table, it's very important to make sure it's listed as a foreign key. Okay, so let's step through some illustrations of what happens when you create a table. Basically, if we were to run those two statements, you'd get two tables created and they'd be empty, just like you see here. I'd have an institutions table, it would have the 4 columns I specified, I'd have the positions table, and it would have the columns I specified, but we've not done anything with them other than creating them, so they would be empty for the time being. If we wanted to add data, we'd use what's called an insert statement, and it sort of is laid out like this. We have insert, the keyword into, and then we list the table, in this case institutions. We list the columns that we want to populate data into. In this case, it's the type, the name, and the department. Notice that the primary key is not listed here. Why is that? Well, that's because, coming back up here, notice that it's auto increment. What that means is that whenever I insert into this table, it's going to figure out on its own what to place as that primary key value. So I don't need to specify it when I insert. It'd be a nightmare if I did, right? I'd have to keep track of where I was last time, and I get all these complaints from the database that I'm trying to overwrite a key and so on. So basically, your primary key fields, when you're inserting, as long as you've designed it correctly, you can sort of forget about them. Okay, so in this case, I've said the table, I've said which fields I want to insert into, in this case type, name, and department, and then I've specified a set of values that I want to insert. In this case, there's 3 rows. The first row, the type is going to be academic, the name is going to be MSU, and the department is going to be computer science, and the same flows for the other rows that I want to insert into this table. The same is true of positions, except in the case of positions, instead of specifying these 3 fields, I want to do these 4 fields, right? Notice as well here that I didn't specify all the fields. I don't have to. It would complain only if I had come up here and I tried to not provide information for a field that was flagged as not null. That is to say, if I had come up here and I had tried to not put the start date, there would have been an error because you're not allowed to insert a null value in the start date based on the way we designed this. Okay. So now we have some data. We run those insert statements. We've got some data in our database. And the way that we would know that is we could run a select query. So we do select star, which means everything from our institutions table, and we get some result that looks like this. You have the column headers and you have the data that exists within it. Notice that the institution IDs were created automatically using the functionality that I referenced earlier. But of course, we may not want to select all the fields or all the columns in this case. So we can actually specify which columns we're interested in the positions table, for example, by simply writing them out. I might say I'm interested in only seeing the title and the responsibilities columns from the positions table, and I would get something like you see there. When you want to do a select, there could be circumstances where if your tables get very big, you're interested in understanding what some of the distinct properties of either certain columns, collections of columns, or even your whole database is. And you can do that by including this distinct term after your select. In this case, I've said, let's select the distinct type from institutions. And if you compare what's returned there, which is academic and government, against the kinds of types of institutions that are in this table, you can see it's selected the two distinct types and returned them to me. Oftentimes, of course, when you're doing queries, you don't just want to select everything that's in a table or select everything within a given column of that table, but you oftentimes are interested in putting additional constraints based on the properties of a given row. And that's what a where clause is for. Okay, so here, I'm interested in selecting everything from the institutions. So I want all the columns, that means. But I want to make sure that the type is academic. So if we come down to this select star statement, you can see type academic would give us these institution ID 1 and 2 rows. And I want the department to be like engineering. Notice here a couple of things that I've done are sort of implied by this where clause. First, the where places a constraint so that I'm only going to select where the type is academic and the department is like engineering. So ergo this result here for institution ID 2. But I want to step you through some of the important syntax here. First, notice that the where is all caps, but the and, which is another special term, is lowercase. This is because SQL is not sensitive to keeping things in caps. You can keep it lowercase or caps. It's good for stylistic kind of separation to actually keep these things all uppercase when they're reserved keywords by SQL. Okay, so in this case, you would make the and all uppercase. Of course, this and also implies that where clauses, you can have logical combinations that are implied by them. So in this case, I was able to combine these two constraints, type equals academic and department like engineering. Also notice another piece of syntax here, that the like clause is used to take a field in this case, or look at each field, and to say, I want to sort of not look for an exact match there, but look for a partial match. In this case, I was looking for the term engineering anywhere within that department. The way that you do a search like that is through the use of this parentheses, which is sort of like a wildcard character when you're doing a string match or a string search. So it says, hey, if engineering shows up anywhere in this department column, it satisfies the criteria, and take it. SQL also gives you a way to order the information you get back. So you might want to sort your results in ascending or descending order based on a number of things. It could be, some ID, it could be a title, it could be a start date or an end date. In this particular example, I'm showing you selecting everything from the positions table, and I've ordered it by the start date. And as you can see here, now we've got the start date so that 1210 is at the bottom. When we just regularly select from positions, the 1210 start date entry for the instructor is in the middle. There's also a cool capability within SQL that allows you to do if then else kinds of statements. So that's called a case in SQL. And so you can add these as though you were pulling a column from the table. Okay. So what I've done here in this example is I'm selecting the title and the responsibilities from the positions table. And then you can see there's this big case block. What this case block does is it's going to construct a single additional column. So everything that's encased by the case creates this one column that's called current. And I know it's going to be called current because of this keyword as. So when you have an and as, these two together say, hey, name whatever comes out of this case statement, put it within a column called current, which you see here. Okay, so how do I know what goes into that current? Well, I've got some if then else logic. I say first when the end date, if we come back to this table, notice that the end dates here were null, right, in the positions table. Well, I said when that end date is null, then I want you to generate a 1 in that column. Otherwise, I want you to put a 0. So no surprises, these were always null, and so therefore the current is always 1, which is what I asked for. Now, of course, it may be the case that as you're going through and dealing with data, you'd want to do updates. So for example, I might want to update that end date, okay, the same one that was always null. And you can use an update statement for that in SQL to do it. In this case, I'm saying let's update the positions and set the end date to a value. Here's the value, 2021-1-1. And I want to do that where, so which rows do I want to update the end date for? Well, I want to do it for the rows where the institution ID is, and then you can see we have an in clause. An in clause set, basically you open a parentheses and you put a set of values in there that says, hey, if the institution ID is anywhere in this set, then you're good to go. So in this particular case, we've done what's called a nested query, because I said I want an institution ID that's anything that's returned by this query. Select institution ID from institutions where name is equal to MSU, which generates what you see here on the right-hand side. Effectively, what this query does is it gives me 2 values, 1 and 2. And so the query then says, let's update the positions and set the end date equal to this, where the institution ID is 1 or 2. That's what this query does. And so, well, if you look at the result here on the bottom, what do you see? Oh, look, where the institution ID was 1 or 2, in this case 1, it's going to come and it's going to update the end date. Okay, so now if I reran that query from before, where I was selecting title and responsibilities using that and had that case statement to say, if it's null, then set it to 1, otherwise set it to 0, end is current, you can see that we get a corresponding update in current, okay? There's other things that you can do on your tables in SQL. You can, for example, select min and max values on your columns. In this case, I'm showing you from the positions table that we created, selecting the min start date and the max start date, okay, which is 2020-1-1 and 2020-12-10, as you can see down in that bottom table. You can also do other analytic operations on the tables, such as counting the number of rows under some circumstances. In this case, I'm saying, hey, I just want to count the total number of rows. That's what the star means. So count star, count all rows. And I'm going to name that, that result of this count as a new column called cool positions. Okay. And I want it to only do this count where the responsibility has the word cool in it. So if you come down here, you can see that there's 2 rows exactly where the word cool shows up. There's for the researcher position, I say I do cool research, and for the instructor position, I say I teach cool classes. Because cool shows up twice, therefore the consequence of this query is I get 2. Okay, and lastly, and this is sort of perhaps the most important part of everything you will do in SQL, is the ability to join tables. That's to take information from one table and using the key from another table, glue the 2 together. You do that with something that's called a join operation. And what I've got is an example of a join operation here. So first of all, I'd like to step you through some of the syntax of this. It's a little different from what you saw previously because I'm exposing you to a couple of new concepts. First, notice that in all the previous examples, when I had a from statement, like institutions or positions, I didn't have like an I or anything following it. It just said institutions. Well, there's a way when you're writing your queries to come up with a shorthand way to refer to this table by putting a space and giving it a name. In this case, I gave institutions a shorthand name of I, so that it'd just be easier for me to deal with it when I want to write stuff later. Okay, and I end up using that here in the select. I say from that I table, I want to select everything. But then also note that I've got this P table that I want to grab the title from. Okay, well, let's see how we got that P table. We got that through joining. Okay, we joined specifically on positions, which we decided to call P. And how are we going to do the join? This join says, well, tell me exactly what two fields you're going to glue together so that you can get these two things matched up. And you tell it, well, hey, join, the inst ID from the institutions table is the same as the inst ID from the positions table. So given those two things, you can glue the two tables together, and consequently, you would get a table like you see down here. So if you understood everything I've taken you through, you should know most of actually what you'll need in order to develop relational database systems for powering your web applications backend. There's some additional considerations for these database systems that we're going to speak about a little later in the semester, such as the indices and things, which I've intentionally not sort of taken you through on the SQL side here yet. Those considerations become particularly important when you want to scale your web application to be very large or service a kind of a global kind of audience. But for the purposes of introduction, we've sort of gotten to the end of relational databases. So thank you for your attention. And as always, feel free to reach out to me if you have any questions.